Hello and welcome back. We concluded our last session with an introduction of Euler's formula, what Richard Feynman called the most remarkable formula in mathematics. We're going to pick it up right from there, starting with a proof of it. There are different ways of going about proving Euler's formula. I like the one that makes use of Taylor and Maclaurin series expansions. So let's start with a discussion of what those are. Let's take a function f of an arbitrary variable x. As an example, we will take x to be time and f of x to be distance as a function of time. Remember that this is just an example to illustrate the general concept, which applies to any differentiable function of any variable. Let's say we know the distance at some specific time a, and we want to determine the distance at some later time x. We can take the instantaneous speed at time a, which is the first derivative of distance, multiply it by the time interval x minus a to get the distance traveled over that interval, and add it to the distance at time a. If our speed is constant over this interval, then this will give us exactly the distance at time x. If not, then we need to account for the acceleration at time a, which is the second derivative of distance. If the acceleration is not constant over the interval, then we need to take the third derivative into account, and so on through the nth derivative. The sum of all of these terms as n goes to infinity is called the Taylor series expansion of the function about the value of x equals a, named after the English mathematician Brooke Taylor, who introduced these series expansions in 1715. If you are interested in learning more about Taylor series expansions, why they look the way they do, and why they are useful, there is an excellent video on the YouTube channel 3 Blue, 1 Brown at the link shown here. I have provided this link in the video description below, and I have also provided it as a card that you can click on above. A special case of the Taylor series evaluated at x equals 0 is called the Maclaurin series, named for Scottish mathematician Colin Maclaurin. We'll be making use of the Maclaurin series right now. Here is the Maclaurin series expansion of the cosine function. Recalling that cosine of 0 equals 1 and sine of 0 equals 0, the terms with the odd exponents of x all go to 0, and we are left with only the terms with the even exponents. Here is the Maclaurin series expansion of the sine function. This looks similar to the expansion of the cosine function, but here the terms with the even exponents of x go to 0, and we are left with only the terms with the odd exponents. Here is the Maclaurin series expansion of the imaginary exponential function. J is defined as the square root of -1, thus j squared is -1, j to the third power is minus j to the fourth power equals 1, and the cycle repeats for higher powers of j. We make these substitutions and separate the terms into groups of real and imaginary components. The group of real terms corresponds to the series expansion for cosine of x, and the group of imaginary terms corresponds to the series expansion for sine of x. Thus, we can write that e to the power of jx equals cosine of x plus j sine of x. Quod erat demonstrandum. Now, to my mathicist's mind, this is simply a thing of beauty. It's every bit as beautiful as looking at a painting by Rembrandt or listening to a piece of music by Mozart. Let's return to our unit circle, but instead of the xy plane, we will put it in what is called the complex plane. The horizontal axis is called the real axis, and the vertical axis is called the imaginary, or j-axis. We'll draw a segment from the origin to a point on the unit circle that forms an angle theta with respect to the positive real axis. The point on the unit circle represents a complex number, whose real component equals cosine of theta, and whose imaginary component is j sine of theta. From Euler's formula and the proof that we just walked through, we can say that this is equal to e raised to the power of j theta, which includes both the real and imaginary components of our complex number. If we take the first real imaginary pair from the Maclaurin series expansion of e to the j theta, then add successive pairs, we see that we start to get a good approximation of the unit circle. It looks pretty good with 5 Maclaurin pairs, and it will just keep getting better as n approaches infinity. This provides a graphical illustration that Euler's formula is not simply something we use for notational convenience. It is a true mathematical equality that gives us an extremely powerful tool for analyzing sinusoidal functions. Now let's take our angle theta and flip it about the real axis to give an angle of minus theta. This gives a point on the unit circle that we can express as e to the minus j theta, which equals cosine of minus theta plus j sine of minus theta. Because cosine is an even function and sine is an odd function, we can rewrite this as cosine theta minus j sine theta. This is called the complex conjugate of e to the j theta. The two complex numbers have the same real part, and their imaginary parts have opposite signs. Real and imaginary components of a complex number can be expressed as equal parts of a complex conjugate pair. Cosine theta equals 1/2 times e to the j theta plus e to the minus j theta, and j sine theta equals 1/2 times e to the j theta minus e to the minus j theta. Now let's make things even more interesting. Let's rotate our point on the unit circle counterclockwise at some constant rate that we will call the frequency f, typically expressed in cycles per second or hertz. The angular frequency omega equals 2 pi times f because there are 2 pi radians per cycle. E to the j omega t defines a rotating motion in the counterclockwise direction along the unit circle in the complex plane with a constant angular frequency of omega radians per second. Cosine of omega t is the projection of e to the j omega t onto the real axis. It may be thought of generally as kinetic energy. Sine of omega t is the projection of e to the j omega t onto the imaginary axis. It may be thought of generally as potential energy. Now let's rotate our point on the unit circle in the clockwise direction, which we can express as e to the minus j omega t. The cosine projection is unchanged because it is an even function, and the sine projection has the opposite sign to what it had for counterclockwise motion, because it is an odd function. If theta is our initial phase angle for our counterclockwise rotation, we include it in our expression as shown here. If minus theta is our initial phase angle for our clockwise rotation, our expression becomes e raised to the j times the quantity minus omega t minus theta. We can rewrite this as e to the minus j times the quantity omega t plus theta, expand it into its cosine and sine components, and we see that it is the complex conjugate of our expression for counterclockwise rotation. The significance of all this is that a sinusoidal waveform can be thought of as a linear projection of a circular rotation with a constant angular frequency of omega equal to 2 pi times f. In the case of rotating machinery, such as motors and generators, the circular motion is clearly quite literal. The point is that all sinusoidal and periodic waveforms in any application are modeled as a circular projection, as directly implied by the use of the term omega used to represent angular frequency. Indeed, the basic unit of frequency, hertz, is equivalent to cycles per second, which by its very nature indicates a cyclical or circular motion, whether real or implied. You may well ask, why must we come up with this abstraction of circular motion when it isn't real? Why can't we just deal with sinusoids directly? A fair question, to be sure. But to my mind, a sinusoidal waveform makes a lot more intuitive sense when viewed as a linear projection of something rotating at a constant speed. Whether real or implied, The circular motion helps our understanding of sinusoids and periodic waveforms, and it's a very powerful tool that we will be using a lot. And to give you a sneak preview, positive and negative frequency components, plus and minus omega, are included in Fourier analysis when using complex exponentials, and we will explore this further in upcoming sessions. Here are some useful conversions around our unit circle. E to the j times 0 equals 1. E to the j times pi over 2 equals j. E to the j times pi equals negative 1. E to the j times 3 pi over 2, or e to the minus j times pi over 2, equals minus j. And e to the j times 2 pi is the same as e to the j times 0, which equals 1. Let's take a closer look at theta equals pi. We can rearrange the terms to get e to the j times pi plus 1 equals 0. This is called Euler's identity, also named for Leonhard Euler, and it is not to be confused with Euler's formula discussed earlier. This identity is noteworthy because it links 5 fundamental mathematical constants: e, j, pi, 1, and 0. Many people have waxed poetic, or mathematical, about Euler's identity over the years. Paul Nahin of the University of New Hampshire calls it of exquisite beauty. So, why do we mathicists dig our imaginary exponents? Well, when we take the derivative of e to the j omega t, we get j omega times the original function, e to the j omega t. When we integrate, we get 1 over j omega times the original function, e to the j omega t. Derivatives and integrals of the exponential function give back a form of the original function, which is simpler than dealing directly with sinusoidal functions. A common operation is to multiply a complex number by its conjugate. We will encounter this quite a bit with Fourier analysis. With the exponential functions, we can complete this in a single step. We see right away that the exponents cancel to 0, leaving a value of 1. With the sinusoidal functions, we'll eventually get the same answer, as we must, but it takes a few additional steps. It's not especially difficult, but it's a bit more cumbersome, and I like the first way better, and we'll be making ample use of it. Another advantage of the exponential function is that the phase term can be factored out as a constant. This facilitates separate manipulations of the frequency term. This is considerably more cumbersome with sines and cosines. So, to summarize imaginary exponents and Euler's formula, once you wrap your brain around imaginary exponents, they facilitate much more straightforward mathematical operations than do sinusoidal functions. We mathicists dig them because in the long run, they make things simpler, not more complex. And the importance, utility, truth, and beauty of Euler's formula simply cannot be overstated. Let's return to our unit circle in the xy plane, and let's revisit how we define our angle theta, and put it in terms of the area subtended by it. The area is the fraction of the full circle, given by our arc length theta divided by 2 pi radians for the full circle, multiplied by the total area of the circle, pi r squared. Because it's a unit circle, r equals 1, and the pi terms cancel, and we see that the area equals theta over 2. The unit conversion from radians to area is covered by the r squared term, which again is 1 for our unit circle. We'll come back to this presently. Recall that the defining equation for our unit circle is x squared plus y squared equals 1, which we can rewrite as cosine squared of theta plus sine squared of theta equals 1. Now let's look at the unit hyperbola, whose defining equation is x squared minus y squared equals 1. So yes, we are going to talk a little bit about hyperbolic trig functions. Let's draw a segment from the origin to some point on our hyperbola. So, what is the hyperbolic angle A associated with this point and this segment? To define A, we need to look at the hyperbolic sector formed by the segment, the hyperbola, and the x-axis. The hyperbolic angle is defined as A for a hyperbolic sector with area A over 2. Stated another way, the hyperbolic angle is defined to be twice the area of its hyperbolic sector. This seems like a weird definition taken on its own, but it makes a lot more sense when compared with the alternate definition of angles in the unit circle that we just discussed. Now that we have our definition of A, that becomes our argument for our hyperbolic functions. The x-coordinate of our point on the hyperbola is hyperbolic cosine of A, and the y-coordinate is hyperbolic sine of A. We can substitute these terms into the defining equation to get hyperbolic cosine squared of A minus hyperbolic sine squared of A equals 1. This is clearly similar to the relationship for standard sine and cosine functions, but this time with a negative sign. Hyperbolic tangent is defined as hyperbolic sine divided by hyperbolic cosine, again similar to their standard trig counterparts. Hyperbolic cosine of A equals 1/2 e to the A plus e to the minus A. Hyperbolic sine of A equals 1/2 e to the A minus e to the minus A. In general, A may be a complex number, but here is a graph of the hyperbolic sine, cosine, and tangent functions for real values of A. The first question regarding our expressions for hyperbolic sine and cosine is, do they satisfy the defining equation? Well, it's very easy to show that yes, they do. But the next question is, do they give a hyperbolic sector area equal to A over 2? Well, indeed they do, but the proof is non-trivial. I highly recommend that you watch the video by Dr. Trefor Bazett, Why Hyperbolic Functions Are Actually Really Nice. I have provided the link in the video description below, and I have also provided it as a card that you can click on above. Hyperbolic trig functions are used in the analysis of lossy transmission lines, which we will discuss in the next session. As I stated before, in general, A may be a complex number. But if A is purely imaginary, something very interesting happens. Hyperbolic cosine reduces to the standard cosine function. Hyperbolic sine reduces to j times the standard sine function. And hyperbolic tangent reduces to j times the standard tangent function. So, a purely imaginary hyperbolic trig argument reduces these functions to their standard trig counterparts. This is very useful for the lossless transmission line simplification, which we will also address in the next session. The inverse hyperbolic cosine of x equals the natural log of x plus the square root of x squared minus 1. The inverse hyperbolic sine of y equals the natural log of y plus the square root of y squared plus 1. You've seen this inverse hyperbolic cosine function before in the expressions for inductance and capacitance of a parallel wire transmission line, and you'll see it again in the expression for the characteristic impedance. When we rearrange the terms in our defining equation, we see that those funky square root terms inside our logarithm arguments probably did not appear by accident. We'll wrap up this session with a quick refresher on some vector calculus basics. In Cartesian coordinates, a vector is expressed in terms of its x, y, and z components. The dot or scalar product of a pair of vectors a and b is defined as the product of their x components plus the product of their y components plus the product of their z components. The geometric interpretation is that it is the product of the magnitudes multiplied by the cosine of the angle between them. The first example of this that many of us learn is work, defined as the dot product of the force vector F with the displacement vector d. As an example, if you are trying to move an object on a track that is constrained to move only in the horizontal direction, and you are pulling up on it with a rope at an angle of theta with respect to the horizontal direction, only the horizontal component of the force vector, F cosine theta, will be able to do any work to move the object. Now let's look at the cross product of vectors A and B. The geometric interpretation is that its magnitude is the product of the individual magnitudes multiplied by the sine of the angle between them. The first example of this that many of us learn is torque, defined as the cross product of the moment arm r with the force vector F. If you apply a force F at some distance r from a pivot point, r is defined as the moment arm. If the force is applied at an angle of theta with respect to the direction of r, only the force component perpendicular to the moment arm, F sine theta, will apply any torque to rotate the object about the pivot point. In this example, the rotation will be counterclockwise, and per the right-hand rule, the torque vector will point out of the screen. Throughout electromagnetics, we encounter the del operator. The gradient of a scalar field V, shown as del V, gives the spatial variance of the field. The divergence of a vector field A, shown as del dot A, gives the net outward flux of the vector field per unit volume around a point as the volume tends to zero. The divergence theorem states that the volume integral of the divergence of a vector field equals the total outward flux of the vector field through the surface bounding the volume. The divergence theorem provides the relationship between the integral and differential forms of Gauss's law. The curl of a vector field, shown as del cross A, is defined as the tendency of a vector field to curl or rotate about a point in space. Stokes' theorem states that the surface integral of the curl of a vector field over an open surface equals the closed line integral of the vector along the contour bounding the surface. Stokes' theorem provides the relationship between the integral and differential forms of Ampere's law and Faraday's law. And lastly, I promised you a proof of this identity that we used in the Maxwell's equation session, which states that the curl of any vector field A equals the gradient of the divergence of A minus the vector Laplacian of A, shown as del squared of A. It's actually a simple proof that requires only a few steps. We use the definitions of gradient and divergence to write out this expression for the gradient of the divergence, and the vector Laplacian is defined by this expression. These expressions are where we want to end up. The curl is given by this expression. We regroup terms, then we add and subtract a common term to each group as shown here. We separate this into two groups, and we see that the first group equals the gradient of the divergence, and the second group equals the vector Laplacian. Thus, the curl of A equals the gradient of the divergence of A minus the vector Laplacian of A. Quod erat demonstrandum. Clearly, mathematics is used throughout electromagnetics. It provides powerful tools to help us understand the fundamental physics. It provides endless fodder for us mathicists, guilty as charged, but I submit that even non-mathicists should have at least a high-level understanding of the equations that we use in order to apply them appropriately. In particular, I encourage you to embrace Euler's formula and imaginary exponents. They are your friends. And while hyperbolic trigonometry functions may not be your friends, you should consider inviting them over for dinner once in a while. They are your curmudgeonly uncles who may someday leave you money, or outlive you. We will directly apply many of these tools in upcoming sessions on transmission lines, Fourier analysis, and dipoles, to name a few, and I strongly encourage you to try to learn to hear the music of it, because there is plenty of it to be heard. See you next time.